A sphere inside a spherical shell. A solid insulating sphere of radius a carries a net positive charge q uniformly distributed throughout its volume. A conducting spherical shell of inner radius b and outer radius c is concentric with the solid sphere and carries a net charge minus 2q. Using Gauss Law, find the electric field in the regions labeled 1, 2, 3, and 4 in the figure. 1 inside the solid insulating sphere, 2 in between the conducting shell and the sphere, 3 inside the conducting shell, and 4 outside. And the charge distribution on the shell when the entire system is in electrostatic equilibrium. So how is this charge minus 2q distributed over this shell? So let's start with region 1 when r is less than a. When r is less than a, we can form this Gaussian surface with radius r less than a. Let's call this Gaussian surface 1. And we can calculate the charge enclosed by this surface. So this will be q inside. That is the charge density rho multiplied by the volume 4/3 pi r cube. And the charge density, because we have a uniform distribution of charge in this insulating sphere, it's the total charge q divided by the volume of the sphere, which is 4/3 pi a cube. So this multiplied with 4/3 pi r cube will give us our charge enclosed by this sphere. So 4/3 pi's will cancel, and we will find the charge enclosed to be q in is q times r cube over a cube. Okay, now we can write Gauss law. The closed surface integral E dot dA, the flux through this closed surface, is equal to, now we have a uniform charge distribution here that will create an electric field which will be pointing radially outward because it's a positive charge. So electric field and dA vectors will be basically parallel to each other. So these will be the dA vectors that are pointing radially outward. So therefore, this integral E dot dA is E dA cosine 0, so that's E dA. And the electric field will only be a function of r, so we can basically take the electric field outside and calculate the surface area dA, integral dA, that's E times 4 pi r square, is equal to charge enclosed, which is q times r cube divided by a cube. All right, so this r square will make this r cube r, and we will be left with an electric field in region 1 when r is less than a, q over 4 pi. Okay, so here we have also an epsilon 0 because it's charge enclosed divided by epsilon 0, that's Gauss law. So electric field for r less than a will be then q over 4 pi epsilon 0, which is Coulomb's constant k times q, and it's r divided by a cube in r hat direction, which is pointing radially outward. All right, so let's move on to region 2. Region 2 is now in between the conducting shell and the insulating sphere, and this basically has a charge enclosed inside, which is Q. So in region 2 we have R between A and B. The charge inside is just Q. So we can write Gauss law. The total flux E dot dA in this closed surface is basically the same thing here. The dot product is EdA. So here the dA vectors basically point radially outward, and also the electric fields point radially outward. So we have electric field only as a function of r, so it's a constant on the surface, E integral dA, which gives us E times 4 pi r squared. That is the charge enclosed, total charge enclosed is Q, divided by permittivity of free space. So this gives us our final answer in region 2 when r is between A and B. The electric field is K Q over r square in r hat direction. K is 1 over 4 pi epsilon 0. Now in region 3, we're inside a conductor. So we know that inside a conductor at equilibrium, we must have zero electric field, otherwise the mobile electrons would move to establish equilibrium. So inside the conductor, the electric field that's in the region between B and C is in zero r hat. So that's basically no electric field inside a conductor at equilibrium. All right, so let's move on to region 3. Now region 3 is outside the conducting shell. So what is the total charge enclosed now outside this conducting shell? Well, we were told that this conductor is charged to minus 2Q, and this insulating sphere is charged to plus Q. So we would have a total charge in the region R greater than C. Charge enclosed will be minus 2Q plus Q, which is minus Q. Now we can write Gauss law. Closed surface integral E dot dA is basically EdA, again, cosine 0. Electric field is a constant on the surface, so that is E times 4 pi r square is equal to charge enclosed, which is minus Q, divided by epsilon 0. Therefore, we find the electric field in the region 4 r greater than C to be minus K Q over r square r hat. So it's in minus r hat direction. So here the electric field would be pointing basically in this direction. So this would be electric field R greater than C, pointing radially inward. Now, what is the charge distribution on the shell? Now, in region 3, since in region 3, that is inside this conducting shell, we have Gauss law telling us EdA, E dot dA is equal to Q in over epsilon 0 is equal to 0. So if I take a Gaussian surface, so this gray surface here, spherical Gaussian sphere, So this will give me the charge enclosed to be Q. There is the plus Q due to the insulating sphere plus X is equal to 0. So X is equal to minus Q. So this is telling me that I already have plus Q inside, but then I must have a minus Q at the inner surface so that the total charge will be 0, so that the electric field will be 0. So the conclusion is that minus Q resides on the inner surface of the shell, and minus Q, the remaining minus Q, resides on the outer surface of the shell. So the total charge in the shell will be minus 2Q on the shell. Okay? Now, if I had a modification to this problem, if the inner sphere, the insulating sphere, which is R less than A, region 1, were conducting, electric field for R less than A would be equal to 0, and the charge plus Q would distribute uniformly over the surface of the sphere. Because the electric field inside this shell then would have to be 0. So that means if I take this Gaussian surface inside with no electric field, there must be no charge inside. So all the charge would be on the surface of the sphere, and that would be the only modification here. We would have a uniform charge distribution on the surface and 0 electric field inside the conducting sphere. Okay, so in this problem we looked at an insulating sphere inside a conducting shell. So these are concentric. So the radii are A, B, and C. So A is the radius of the insulating sphere, B is the radius of the inner shell, and C the outer shell. So we want to know the electric field inside this insulating sphere, in between the sphere and the shell, inside the shell and outside the shell. For each of these regions, we basically form a Gaussian surface. So we have 4 Gaussian surfaces here. In region 1, the charge enclosed by our Gaussian surface is the uniform charge density Q over 4/3 pi a cube multiplied by the volume of the sphere 4/3 pi r cube. So writing Gauss law, the total electrical flux E dot dA for this closed surface is charge enclosed over epsilon 0. Charge enclosed turns out to be QR cube over A cube, so we find KQR over A cube R hat. So the electric field increases linearly with radius distance from the center. In region 2, we have charge enclosed equal to Q, so we have KQ over R square R hat as the electric field. So electric field also points radially outward. In region 3, we're inside a conductor. Mobile electrons basically guarantee that the electric field inside is reduced to 0 at equilibrium, because the entire system is in electrostatic equilibrium here. In region 4, outside the spherical shell, the total charge enclosed by our Gaussian surface is minus 2q plus q minus q. So this gives us minus kq over r square r hat. The electric field points radially inward outside. Now, what is the charge distribution on this shell? Because if I form a Gaussian surface here, the electric field inside the conductor is 0, E dot dA is 0, which gives me the charge enclosed plus Q minus Q. So the total charge enclosed should be 0, so that tells me that the inner surface has a uniformly distributed minus Q charge. Since the total charge in the conducting shell is minus 2Q, the remaining minus Q must reside on the outer surface of this shell. And if I modify this problem so that the insulating sphere inside is basically conducting, then the electric field for r less than a would be 0, and the charge plus q would be distributed uniformly over the surface of the conducting sphere.